All right, let's jump into another deep dive. This time we're going through those physics notes, the ones on electricity, magnetism, and all that good stuff. The electromagnetic spectrum.
Yeah, those fundamental building blocks.
Exactly. And I know our listeners are pretty familiar with the basics, so
We're going to go a bit deeper.
yeah, we're going to try to hit those aha moments, the stuff that really makes you think. So I was looking through the notes, and right off the bat, there's this example about transmitting 100 kilowatts of power over a 100 kilovolt line, and that somehow leads to a 1 amp current.
Hmm.
I mean, why is that important? What's the takeaway there?
Well, it really highlights why we use those high voltage transmission lines in the first place.
Okay.
You see, whenever electricity has to travel any distance, you're going to lose some energy along the way. It gets lost as heat because of resistance in the wires, and the higher the current, the more power you lose.
So it's kind of like trying to squeeze a ton of water through a tiny pipe.
Yeah, exactly. You lose pressure, you lose energy, it's just not efficient.
So by cranking up the voltage, they're actually reducing the current to prevent those losses.
Precisely. It's all about finding that sweet spot to get the power where it needs to go without wasting a bunch of energy.
Pretty smart.
It's a really clever application of physics.
And those big transformers you see on power poles, are those the things doing the voltage boosting and then stepping it down again for us to use safely?
Yep, that's exactly what they do. They step the voltage up for those long-distance hauls and then step it back down so it's safe to use in our homes.
Huh. I always wondered what those things were all about. But okay, so we've got electricity flowing, but then the nodes sort of shift gears and start talking about magnetism, which for the longest time I always thought of as something totally separate,
Right. For centuries, they were considered completely separate forces.
like oil and water.
But then comes the 19th century, and this guy named James Clerk Maxwell comes along, and, well, he kind of blows everyone's mind.
Okay, what did he do?
He shows that electricity and magnetism are actually intertwined. They're not separate forces, they're two sides of the same coin. And get this, he comes up with these equations,
Yeah.
and they predict that any change in an electric field actually creates a magnetic field and vice versa.
So like they're constantly creating each other, like
Yeah.
some kind of a crazy dance.
That's a great way to put it. It's like this constant interplay between these two forces.
Wow.
And the craziest part is, Maxwell also calculated the speed of these electromagnetic disturbances.
Oh, I know where this is going.
And, you guessed it, it turned out to be the speed of light.
Yeah, that's mind-blowing. That must have been a huge moment in physics when they realized that light itself is just an electromagnetic wave.
Totally revolutionary.
Mm.
And it opened up this whole new understanding of, well, everything. Because it turns out light is just one small part of this much bigger picture, this thing we call the electromagnetic spectrum.
Right, the spectrum. It's like a giant rainbow, but
Right.
invisible for the most part.
Yeah.
But how do we go from, like, sparks and stuff
Yeah.
to things like smartphones and Wi-Fi? I mean, that's a huge jump.
Well, you got to start somewhere, right? And those early experiments with sparks were actually the first steps toward understanding radio waves.
Radio waves.
Yep, the longest waves in the spectrum. They carry the least amount of energy, which is why you can listen to the radio all day without, getting cooked.
That makes sense. But then how do we get to something like, say, a microwave oven?
Ah, so as you move along the spectrum, the waves start getting shorter and they pack more of a punch in terms of energy. Microwaves, they're a perfect example. They have a higher frequency than radio waves, and they're tuned to specifically excite water molecules.
So that's how a microwave heats up food, by basically making the water molecules go crazy.
Exactly. It's all about those vibrating water molecules generating heat. That's why you can heat up a cup of coffee in a microwave in just a few seconds.
Wow, that's pretty cool. And it really shows how different frequencies of these electromagnetic waves can have such vastly different effects.
It does. It does.
All right, so we've got radio waves, we've got microwaves, and next up I know we've got infrared, which I always think of as, heat, like standing next to a fireplace or using those night vision cameras.
Right, exactly. It's all about heat and molecular vibrations. Then comes visible light, that tiny sliver of the spectrum that our eyes can actually see.
And all the colors we see, it just comes down to different frequencies within that tiny little sliver. It's crazy to think that's all we can see, just a tiny fraction of this vast spectrum. And beyond visible light, I know things start getting a bit more intense, like get into ultraviolet rays, X-rays, and then the really heavy hitter, gamma rays.
You got it. And each of these has even more energy. Ultraviolet rays, they can give you a sunburn even though you can't see them.
Yeah, that's always a bummer.
And X-rays, they're powerful enough to penetrate our bodies, which is why we can use them to see our bones.
Pretty wild when you think about it.
And gamma rays, they're the real powerhouses coming from things like nuclear reactions. It's incredible, really. All these different waves behaving so differently, yet they're all part of this one spectrum.
And it's all governed by those equations Maxwell came up with, right?
Exactly.
That's a lot to take in.
It is. And we haven't even gotten to the really interesting stuff yet.
What do you mean?
This is where we start getting into quantum physics and how our understanding of electromagnetism has, well, evolved.
Okay, quantum physics. I'm a little nervous, but I'm definitely intrigued.
Don't worry, we'll take it slow. Let's start with a phenomenon that really puzzled physicists for years, something called the photoelectric effect. It basically shows that light can knock electrons out of metal.
Yeah, I remember reading about that. It's almost like light is acting like a particle instead of just a wave, right?
You're picking up on it quickly. This was a huge deal because it challenged the traditional understanding of light, and it led to Einstein's groundbreaking idea that light can act like both wave and a particle.
Both. How is that even possible? It's like saying a baseball can be a curveball and a fastball at the same time.
It's definitely mind-bending, but that's quantum physics for you. And these particles of light, they're called photons, and their energy is directly related to their frequency.
So the higher the frequency, the more energy packed into each photon.
You got it.
Which would explain why gamma rays are so much more powerful than, say, radio waves.
Exactly.
Wow.
And this, my friend, is just the tip of the iceberg when it comes to the mysteries of quantum physics.
Okay, so before we went off on that quantum physics tangent, we were talking about how light can be both a wave and a particle.
Right.
Which still, I gotta say, kind of feels like something out of Star Trek.
It's definitely one of those things that makes you question everything you thought you knew about, well, reality.
Exactly.
Yeah.
But, okay, so after Einstein kind of dropped this bombshell on the physics world, did anyone, try to actually prove it? Or was it just a theory for a while?
Well, that's where this guy Heinrich Hertz comes in.
Hertz? Like the rental car company?
Yep, that's the one.
No way. I had no idea there was a connection there.
It's a fun little bit of trivia. But anyway, Hertz was this brilliant German physicist, and back in 1887, he actually did some experiments that kind of blew the doors wide open when it came to electromagnetism.
What kind of experiments?
Well, he was the first person to actually generate and detect radio waves in a lab.
Radio waves, like using sparks.
Exactly. Remember how we were talking about those early experiments with sparks?
Yeah.
Well, Hertz figured out a way to create controlled sparks.
Yeah.
And use them to actually produce radio waves. And then he built a receiver that could pick up on those waves.
Wow.
And guess what? He proved that they travel at the speed of light, just like Maxwell had predicted.
So he basically proved that these invisible electromagnetic waves are real.
Yep.
And that they can travel through the air.
Exactly.
Wow. That's a pretty big deal.
It was monumental. I mean, his work basically paved the way for, well, everything. Radio, television, and eventually all the wireless technology we rely on today.
It's hard to imagine what the world would be like without his contribution.
It really is.
It's just amazing to me how something as simple as sparks could lead to such a revolution.
It is, isn't it? And the thing is, we're still just scratching the surface.
What do you mean?
I mean, researchers are still pushing the boundaries of what's possible with electromagnetic waves, and the applications just keep expanding. It's really an exciting time to be following this field.
So what are some of the areas that you're most excited about? Where's all this research headed?
Well, one area where electromagnetism is making a huge difference is medical imaging.
Yeah, okay.
We've already talked about X-rays.
Right.
But there's also MRI, magnetic resonance imaging, which uses powerful magnets and radio waves to create these incredibly detailed images of the inside of your body.
It's amazing. I actually had an MRI once, and it's just incredible how they can see everything without having to, cut you open.
Yeah, it's pretty remarkable. And the technology just keeps getting better and better.
Really?
Yep. Researchers are developing new MRI techniques that can actually image the brain in real time.
Wow.
So they can study brain activity in incredible detail.
That's mind-blowing.
Yeah.
Are there any other areas where electromagnetism is kind of pushing the limits of what we thought was possible?
Oh, absolutely. Communications technology is another area that's just exploding with innovation, and it's all thanks to our deeper understanding of electromagnetism. Take 5G networks, for example. They rely on higher frequency radio waves to deliver faster data speeds and greater capacity.
So that's why 5G is so much faster.
Exactly. And we're really just scratching the surface of what might be possible.
It's incredible to think that something as fundamental as electromagnetism is still driving such rapid technological advancements.
It really speaks to the power of, human curiosity and the enduring impact of those really fundamental discoveries. And who knows what amazing applications we'll uncover as we continue to explore and unravel those mysteries.
Okay, so now you've got me really curious about what the future holds.
Yeah.
I mean, we've come so far from basic electricity to all these incredible advancements in medicine and communication. What's next?
Well, let's talk about those future possibilities. What could be next for this incredible force we call electromagnetism? So we've talked about how our understanding of electromagnetism has, really shapes the world we live in today.
Yeah.
But what I find really exciting is thinking about what's still to come.
Ooh, okay, give me the sci-fi stuff.
All right, well, imagine a world where you could walk into a room and your phone just starts charging.
Like
No cords, no plugs, just wireless power.
wireless power.
Yep. And researchers are already working on making this a reality.
That sounds like something straight out of Star Trek.
It does, doesn't it?
But how would that even work?
Well, there are a few different approaches, but one that's particularly interesting is using something called resonant inductive coupling.
Resonant what?
Resonant inductive coupling. It's a mouthful, I know.
Yeah.
But basically, it involves creating a magnetic field that resonates at a specific frequency.
Okay.
And when you bring a device that's compatible with that frequency within range, the energy from the magnetic field can be transferred wirelessly.
So it's kind of like those wireless charging pads they have now,
Yeah,
but
exactly.
on a much larger scale.
Precisely. Imagine entire rooms or even whole buildings equipped with these wireless power transmitters.
Whoa,
Your devices would just charge automatically just by being in the room.
that would be amazing. No more hunting for outlet.
No more tangled cords.
I'm sold. What else? What other futuristic applications are scientists looking into?
Well, how about treating diseases with invisible beams of energy?
No, you're just messing with me.
No, I'm serious. Researchers are actually investigating the use of focused ultrasound and various frequencies of electromagnetic radiation for all sorts of medical treatments.
Like what specifically?
Well, they're looking at using focused ultrasound to target and destroy tumors deep inside the body.
Really?
Yep, without having to do invasive surgery.
Wow.
And they're also exploring how different frequencies of electromagnetic radiation, from radio waves to infrared light, could be used to, stimulate tissue regeneration,
Ah.
manage pain, or even treat neurological disorders.
It's mind-blowing to think that we might one day be able to treat diseases with, like, light or sound waves.
I know, it's incredible. It really shows you how much potential there is in this field.
It does. So what about communication? Any crazy futuristic ideas there?
Oh, absolutely. Right now, we rely on our senses, sight, hearing, touch, to interact with the world and communicate with each other.
Right.
But what if we could bypass those senses altogether?
Okay, now you've got my attention.
What if we could communicate directly with the brain using, precisely modulated electromagnetic waves?
Whoa, are you talking about, like, telepathy?
Well, it's not telepathy in the traditional sense, but it's definitely a whole new way of thinking about communication.
I mean, the idea that we could potentially transmit thoughts and ideas directly to another person's brain using electromagnetic waves, that's just...
It's mind-boggling, isn't it?
It really is. It's exciting, but also a little bit scary.
I agree. It raises all sorts of questions about privacy and, the potential for misuse. It's definitely something we need to think carefully about as this technology develops.
Well, this deep dive has been quite a journey.
It has.
We started with the basics of electricity and ended up talking about, like, the future of technology and communication.
It's amazing how much ground we covered.
It is. I feel like I've learned so much about electromagnetism and, how it's impacted our lives and how it could shape our future.
I'm glad to hear that. And for our listeners, if this deep dive has, sparked your own curiosity, keep exploring. There's so much out there to discover about this incredible force.
Absolutely. Dive into those physics textbooks, read articles about the latest research, maybe even consider a career in science or engineering. Who knows? You might be the one to make the next groundbreaking discovery in the world of electromagnetism.
I love that. The world always needs more curious minds.
Well said. This has been a truly electrifying journey through the world of electromagnetism. Thanks for joining us, and until next time, stay curious